welcome everyone for this new SIPTA seminar. So we are very happy today to receive Jason Konek for as a speaker. And now, Arthur, if you want to give us more details about Jason, please do. And happy to leave you.
Thank you, Sébastien. Good afternoon, good morning, wherever you are. Welcome to the SIPTA Seminar. It is my honor and my privilege to introduce Jason Konek. Many of you will know Jason well. Indeed, he is a well-known person in our community because he is a connection bridge between both sides of the imprecise probability community. The philosophers on the one side and the traditional SIPTA community, for lack of a better word, on the other side. Now, Jason is a senior lecturer in philosophy at the University of Bristol. He was trained in philosophy and mathematics, and he did his PhD studies with James Joyce at the University of Michigan in Ann Arbor. There he studied foundational questions about probability theory and decision theory. Inspired by researchers like Teddy Seidenfeld, James Joyce, and others, Jason quickly realized that both sides of the imprecise probability community, the philosophy and the SIPTA side, have much to gain from a better connection. Indeed, I believe that this is very true, and there has been and is incredibly interesting research going on both the sides. So bringing these two communities together has been Jason's goal since then. So Jason moved. First, he took a fellowship as a postdoc with Richard Pettigrew at the University of Bristol. And then after a brief tenure as a professor at Kansas State University, Jason returned to Bristol, where he now works as a senior lecturer alongside a dynamic group of imprecise probability enthusiasts, including Catrin Campbell-Moore, Kevin Blackwell, Giacomo Molinari, and Richard Pettigrew. Together, they form a vibrant hub of research in imprecise probabilities. But Jason also went to work towards his goal of bringing the two parts together. He obtained a prestigious ERC, European Research Council grant, entitled Epistemic Utility for Imprecise Probability, or EPIMP for short. And this allows him to organize multiple conferences and events in Bristol, where he brings together researchers from both sides. He also has invited numerous researchers to Bristol to do a research day, and he has organized the SIPTA Summer School back in 2022. So by doing this, Jason has joined Teddy Seidenfeld, Gert Koolman, and others in the effort of connecting both communities. And Jason is succeeding in this goal. So please join me in giving a warm welcome to Jason. Jason, the floor is yours.
Thank you. And you know, it's a privilege to get to have at least one foot in this community, and to have worked for years alongside Kevin and Arthur on my team. Let me also plug the final EPIP conference that's coming up on December 18th and 19th in Bristol. If any of you are near enough to come and interested, please just send me an email. I'm happy to give you more logistical details. Okay, so with that, we'll get on to it. So the brief for me today, when I was asked to give this talk, was to try to do a bit of a survey of some of the themes that have emerged in philosophy that might be of interest to IP folks. And so I'm not going to focus primarily, indeed at all in the end, on scoring rules, IP scoring rules, which is what the project has focused on developing. Instead, I'm going to look to two themes, one old, one new, from the philosophical decision theory literature, and suggest that both IP folks could benefit from looking at the developments in the philosophical decision theory literature on these fronts, and conversely, if there ends up being sufficient interest, I'm sure that will then feed back into the philosophy community. So I think it would be a mutually beneficial relationship. I am not going to, in the first instance, focus, there are people in the philosophy community like Teddy, like Greg Wheeler and others who are just contributing directly to imprecise probability theory, the kind of cutting edge of imprecise probability theory. I'm not going to focus on that work as much because that's so directly uh, sort of directly focused at the IP community. Instead, I took my task to be trying to highlight some themes that maybe people in the philosophy community who aren't really pitching to IP folks, some themes that might be of interest to IP folks. Okay, so we're going to look at what the assumption of act state independence is. I mean, also spoiler alert, these things are probably going to be topics that you've thought some about. There's not going to be any revelation. It's all I'm going to try to do here is suggest that there are things that we ought to, as folks interested in imprecise probability, think more about, do more to address systematically. Okay, and one is the assumption of act state independence that's built into frameworks like the desirability framework. And the other is a kind of question about how we deal with the incomparability that we value. As imprecise folks, we want to be able to model agents that have incomplete preferences, that when it comes to making choices, end up not rejecting every element of their option set. I want to suggest that we need to think hard about what we do after that, how we end up resolving that incomparability, and what kind of value there is to be gained by having incomparability in our models in the first place. Okay, so topic one, act state independence. I'm going to let me briefly introduce the desirability framework, which I'm sure all of you are quite familiar with. But we're going to start off with a finite sample space and then a linear space of gambles, which we're thinking of as uncertain rewards. So they have some outcome in each state of the world. There's some linear utility scale in the background, and the gamble is the gamble is specifying the utility of that outcome. So we don't know exactly what outcome it's going to yield, but it's going to yield some outcome measured in linear utility. And then we're going to collect up all of the gambles that we think are desirable and put them in a set D. These are the gambles that we prefer to the status quo, and we'll call a set coherent. Just in case 0 isn't in the set, we never prefer the status quo to itself. If it's non-negative and not equal to 0, then it gets to be in the set. It pays out positive utility somewhere in a possibility that we take to be a real possibility, so it better be desirable. If a gamble is desirable, then any positive scaling of it is desirable, and if two gambles are desirable, then their sum is desirable, and that's it. So the first two axioms force the positive orthant to be in our set of desirable gambles. It forces 0 to not be in the set of desirable gambles, and it forces the negative orthant to not be in the set as well. But aside from that, the other two axioms require our set of desirable gambles to be a convex cone. The bigger the set of gambles, the more judgments we've made, and so the more commitments we've incurred, and so the closer we are to having a precise model. So here we're starting on the left with an imprecise model, and as we're widening it out, approaching a half space, we approach an imprecise probability model. The gambles in here, points in the space, are gambles, say on a two-element outcome space, heads or tails. So some point, say over here, Can you see my cursor? Just nod if yes. Okay. So some point over here, say 5, -1 might be the gamble that pays out 5 utils if it comes up heads and -1 if it comes up tails. And the fact that it's in my set of desirable gambles means that I think that that's better than the status quo. And we can have interesting boundary behavior here. So we can have 1/2 of my set of desirable gambles closed and the other half open, which might represent that I think that the gamble's infinitesimally biased towards heads. And in the other extreme, I have the vacuous model where I don't think anything's desirable other than the positive gambles. Okay, so far so familiar. Now let's move on to a case that is going to be the kind of central focus of this first half of the talk. So imagine that you are late to an event and you're going to go park your car somewhere. Maybe this event isn't in the best neighborhood, and you've just parked your car and you walk past an alley and there's a dark figure in the alley. And the dark figure approaches you and offers to sell you protection for your car. And the protection costs 10 pounds, let's say. But you know how these scams go. If you don't buy the protection, you're liable to end up with a broken windshield, and a broken windshield will cost you 400 pounds. So here we might frame the decision problem as follows. There are 2 states of the world. Many of you will object to this. We'll get to that in a moment. 2 ways that things could turn out, 2 states of the world. Either your windshield ends up getting smashed, or it doesn't. And your 2 options here, modeled as gambles, are to buy the protection or to not buy the protection. If you buy the protection and it ends up smashed, then you've got to pay 400 to replace the windshield and the 10 that you spent on the protection. If it doesn't end up smashed, then you've paid out 10 for protection. If you don't buy the protection, well, you're in the same situation with regard to paying for the fixed windshield, but you've not wasted that 10 pounds on the protection. Okay, so if we allow that this is a legitimate way to model the decision problem that we face, then dominance reasoning encoded in D2 of our desirability axioms forces us to prefer G to F. It's guaranteed to be better, and so the gamble G minus F is a positive gamble. Okay, what's gone wrong here? Well, the answer seems obvious. Buying the protection makes it quite likely, or let me put this more neutrally. Buying the protection, if you buy the protection, it's more probable that you'll end up in this state of the world, the one where it is not smashed. So you're let's say quite likely, and you know this, to only have to spend 10 pounds in that case. And if you don't buy the protection, you're quite likely to end up in this state of the world, and so spend 400 on a new windshield. Okay. So how do we respond to this? Well, Savage's response, Savage, the desirability framework is part of a lineage that respects dominance reasoning in virtue of Savage's sure thing principle. Savage also respects dominance reasoning. And so Savage faced this problem. This came up prominently, as we'll see, in discussion with Richard Jeffrey. And Savage's response was that there's really no trouble with dominance here, and if you kind of read Savage correctly, you'll see that there's an implicit assumption that this decision problem is just ill-posed. A well-posed decision problem is one in which the states the probabilities of states are independent of which gamble is chosen. And so we just We just haven't set up the decision problem in the right way. We should reframe it so that we're not in the situation where which gamble you end up choosing affects in some way the probability that you'll be in one state or another. That's fine as far as it goes, but here are two questions that kind of response leaves unanswered. One is that there's an ambiguity between the sense in which the states should be independent of the X. And there's at least this ambiguity, since, as we know, in the IP community, independence is not a univocal notion. Even probabilistic independence or evidential independence is not a univocal notion. But in the first instance, we might ask, is this a broadly statistical or probabilistic kind of independence that we have in mind, or is it a kind of causal independence? And leaving it as a kind of implicit assumption or a proviso that's outside of our theory does little to address and clear up this ambiguity. The second problem is that this is whether states are independent of which gamble is chosen. This isn't something that we can, for the purposes of rendering verdicts about whether an agent's choices are rational or not, this isn't something we should specify exogenously. This is something that ought to depend on the decision maker's views about acts and states, whether in the decision maker's view, the states are either evidentially or causally independent of the acts. And if, again, we leave this as something unmodeled, something outside of our decision theory, then we can't make this part of the agent's belief state precise in any way. It ought to be something that we model, and that verdicts about the rationality of her choices depend on explicitly. Or so say many in the philosophical decision theory community. So if you find yourself convinced by that, then, well, you might wonder what we can do, which frameworks can be modified in some sort of straightforward way to allow for this kind of modeling of the decision maker's views about the relationships between the gambles that she is going to choose between and states of the world. The problem with desirability, and I'm not going to just focus on desirability here. This is a problem for many IP frameworks, but the problem with the desirability framework is simply that there are no choice events around, and so there's no way to model how the agent thinks, either learning or supposing in some other way that those choice events occur, how they affect the decision maker's views about other things, about which state obtains. So I would like to now take you through briefly some of the moves that philosophers have made to jettison this assumption of act-state independence, to build on Savage's framework in a way that you get back. Now, I'm going to focus on Richard Jeffrey and Jim Joyce, both of whom are sympathetic to IP, as you all know, but whose representation theorems for their variants of evidential and causal decision theory, respectively, aren't really focused on imprecision. So they're broadly in the precise traditional Bayesian tradition, but nonetheless, they lift this assumption of act-state independence, get back Savage, Savage's kind of expected utility as a special case when states are independent of acts in the relevant sense, but they apply more broadly, don't require us to frame decision problems in a particular way. So I'm going to say more about Jeffrey than I am about an evidential decision theory than I am about causal decision theory, and I want to dig into Jeffrey's theory in just a little bit of detail here. So one difference for Jeffrey is that we're going to adopt what Fishburne called a monoset framework, but we're just going to think of acts and states and outcomes as all things of the same type, rather than having acts be gambles modeled as functions from a state space into some into some linear space that's measuring outcomes in a linear utility scale, rather than having states be elements of a state space and gambles be things of a different type. We're going to have them all be propositions. So we're going to model the agent's preferences as a relation on some sigma algebra of some sample space. And this preference relation is going to roughly encode the agent's views about the news value of propositions, how good it would be to learn that some proposition is true in the agent's view. And the thing that's special about acts for Jeffrey is they're a special kind of proposition. They're a kind of proposition that the agent can make true through an act of will. Some acts are like that. Some propositions are like that, and those are acts, and some propositions are not. That is something that we leave outside of our formal model. But as far as the agent's preferences go, she has preferences over all propositions, whether they're acts or not, and then her choices are just choices between certain kinds of propositions. And Jeffrey assumes, firstly, that the agent's preferences are an asymmetric weak order. Jeffrey also assumes, I'm going to fudge a few things here. There are some subtleties about null events, non-triviality that I'm going to gloss over. But basically, Jeffrey is lifting axioms from Volcker and assuming A, that the agent's preferences are an asymmetric weak order, B, that they are continuous in the sense that if a sequence of propositions approaches another from below or above in terms of the subset relation, and the agent prefers B to A to C, then for sufficiently large n, she prefers B to AN to C. The second axiom here is an averaging axiom for any two disjoint propositions. If she prefers A to B, if A is better news than B, then A is better news than A, or B, which is better news than B. That seems relatively straightforward. And the same for indifference. If she's indifferent between A and B, then she's indifferent between A or B, and B. They're all of the same news value. One wrinkle here, so I'm following Fishburne's presentation of Jeffrey, but one wrinkle is it might seem here, since we have just A not preferred to B and B not preferred to A, that this is incomparability, but in Jeffrey's framework, we're really interpreting this as indifference. And so it's a way of building completeness into the theory. So there's no imprecision here. This is a complete ordering in the relevant sense. Even though it's not formally a complete ordering, it is treated as a complete ordering. And the bulk of the work is done by the final axiom, which is impartiality. which is a bit of a mouthful, but let me explain it with an example. Easier to see what's going on with this with an example. So suppose that you've got an urn and it's got some number of balls in it. It's got 1 blue ball, 2 red balls, 3 green balls, 4 brown balls. And Arthur has kindly come along and offered to give you money, as he does because he's a generous person. So you're going to randomly draw a ball. If it's blue or red, you get nothing. As always, Arthur's giving you the good side of this bet. If it's green or brown, £100 for you, no cost. I'm just going to describe your preferences here. Intuitively, given that you value money, well, you are indifferent between learning that the ball was blue or red because you get the same thing in either case, which is 0. You are happier to learn the news that it's green than you are blue, or that it's red, because in that case you get £100, and you're happier to learn the news that it's brown than you are that it's blue and that it's red, respectively. And given the setup and the way I've suggestively talked about it, randomly choosing, then you should be happier to learn that it's blue or green than you are to hear that it's red or green. Why? Because when you learn that it's blue or green, let's suppose you're just uniform over the balls, you condition on that, you end up with a higher posterior that it's green, and so a higher posterior that you get £100, than you are if you condition on red or green. And the same would be true if you switch whether green or brown are better to worse, then you'll find that to be worse. So learning blue or green is better news than learning red or green. But now let's change the situation a little bit. Same as before, same payouts. But now, because there are an equal number of blue and red balls, you're indifferent between learning blue or green or red or green. In either case, you condition, you end up with the same posterior for green, the same expected payout, roughly. And the thought is, well, why is that happening? That's happening because the probability of blue and red are equal. They're equiprobable. So learning blue or green, or red or green, those things are equally good news. That happens if and only if blue and red are equiprobable. And in that case, you should also be equally happy to hear blue or brown or red or brown. When you condition on those, you end up with the same posterior for brown. And so the thought is that this pattern of preferences, you're indifferent between blue or red, you prefer, say, green to either blue or red, but you're indifferent between this disjunction, that functions as a kind of test that you view blue and red to be equiprobable. And in that case, you should be indifferent between any disjunction. That is, disjoining blue or red with any incompatible proposition, mutually incompatible proposition. So that's what impartiality says. If we go back, we just have this pattern of preferences here, and these 3 things serve as a test for finding A and B equiprobable, in which case you ought to also have this. That's what impartiality says. Okay. But to really feel the force of impartiality, you have to start, I think, thinking like an evidentialist. All right. And then with those axioms in place, I mean, this is Jeffrey and Bolker differ on some small details, but this is roughly what you get out of Jeffrey's representation theorem. If the agent's preference relation satisfied the axioms that we just listed, then there are two measures. There's a probability measure on the algebra, and there's a signed measure on the algebra, and the signed measure is absolutely continuous with respect to the probability measure. And they jointly represent the agent's preferences in the following sense. And then we can let this function u just be the ratio of the measures and use a general version of the Radon-Nikodym theorem. And what we end up with is that u takes the form of an expected utility operator, a conditional expected utility operator, where this u inside the agent's utilities for states, if you will, is the Radon-Nikodym derivative of m with respect to p. And this thing is, in Jeffrey's system, unique up to fractional linear transformation. Okay, and so what do we have? We have a preference relation, and we have it roughly fully agreeing. We have a utility over states, and a probability function. And what the agent's preferences are encoding is that when she conditions on A, the expected utility of the world, treating kind of U as a gamble. So a single gamble over all states. I don't know which state I'm in, but in different states, there are different, I attach a different utility to that. Conditioning on A makes me have a better view of this gamble than conditioning on B. Okay, so how can we take some of the main lessons from this approach to jettisoning ax-state independence and try to incorporate them into our imprecise probability models? Well, one approach is to do this directly in the Jeffrey style framework, where it's, again, we're modeling the agent's views as preferences over propositions. Jeffrey treats these preferences, Jeffrey implicitly assumes that these preferences are complete. We could just try to provide a weaker axiomization that didn't get us full agreement with a conditional expected utility operator, but got us, say, partial agreement or maybe full agreement with a set of conditional expected utility operators. And Richard Bradley does a version of this. Richard Bradley is a philosopher at the LSE, who I'm sure some of you have met over the years, provides a representation theorem for an imprecise version of evidential decision theory. So Bradley's representation theorem shows that if Bradley here is, instead of working with a strict preference, working with a weak preference ordering and not assuming completeness. What Bradley's representation theorem provides is full agreement with a set of these PM pairs, the things that are, in effect, conditional expected utility operators. But Richard's axiomization involves an axiom of coherent extendability. So he assumes in particular that there's a minimal extension of this weak ordering. And what the minimal here means is that it preserves the strict part of the ordering. That is roughly Jeffrey coherent, satisfies all of Jeffrey's axioms. To my mind, it would be more satisfactory if we could axiomatize coherent partial preference without assuming extendability, but instead characterizing what that sort of extendability amounts to. And then if we had that kind of characterization, we could move on to do things like try to characterize coherent choice functions representable by coherent partial evidential preference relations. As far as I know, this is work that remains incomplete. I'm happy to hear from others in the audience about folks that have attempted versions of this. I'm certainly not, certainly take it to be an open possibility that there are interesting pockets of work out there that I'm just unfamiliar with. Let me canvass a few other ways that you might go to try to incorporate some of the main insights of evidential decision theory into various IP frameworks. If we wanted to do something that was maybe more continuous with desirability, so rather than moving over to the monoset framework, if we want to keep the separation between gambles and states, we could start with a finite possibility space, consider all the gambles on that space, select out some of them, maybe it's all of them, as we implicitly assume standardly implicitly assume, but maybe it's some subset of them that represent the gambles that are really available to me, ones that I can make true through an act of will in Jeffrey's sense. And then we could refine our state space so that now we have our states, our pairs that specified both an element of our original state space and an element of this set of available gambles. And now we've got events around that let us talk about and model an agent's views about which gambles she will choose, and more importantly, for the purposes of evidential decision theory, the probabilistic dependencies between states and the gambles that she chooses. So let's take the set of all bounded gambles on this new refined state space, and I will just here pick out a proxy for the gambles in our original set. The gamble rho G just returns G's outcome in the cases where you choose G and return nothing in cases where you don't. And now let's assume that you have views about gambles in this new state space, and let's assume that your views are captured by a coherent set of desirable gambles. Now, you could handle some of the issues that we've discussed by proposing a choice rule for sets of desirable gambles like interval dominance, and comparing these proxy gambles conditional on the event that they're chosen. So what I mean here is we'll say that an agent prefers one gamble to another when her maximum buying price for the one gamble is greater than the minimum selling price for the other gamble. Or if we want to retain some of the non-Archimedean flavor of sets of desirable gambles, you could say, well, I prefer this gamble to this gamble if, let's say, I would buy this gamble for exactly this price. So not only is it my lower provision, Um, but I would actually um, I would actually um, the lower provision in particular is PF minus that lower provision, or rho F minus that lower provision, is in my set of desirable gambles. So um, I positively prefer this gamble to my maximum buying price, but I wouldn't actually sell the other gamble at that price, or vice versa. So if you can kind of leave that open edge open if you want some non-Archimedean behavior. But in any case, this is just a toy example to suggest that you can recover some of the verdicts, like the ones that we want in protection, though probably interval dominance is not going to be fully satisfactory. So as an illustration, imagine the protection case again. We have two gambles available to us by the protection or not. We expand our state space now to be a four-element state space. And now let's say that we model your opinions by the coherent set of desirable gambles based on this set of probability mass functions. This just encodes that conditional on buying protection, you think it's quite likely that you'll end up in omega 2. That's what this inequality encodes, and this one encodes that if you your view that if you don't buy protection, you're quite likely to end up in the case where your windshield is smashed. In that case, your lower provision for F is greater than your upper provision for G, determined by this set of gambles. And so you ought to prefer F to G. That is, you ought to prefer to buy protection, even though the one dominates, not buying protection dominates. Okay. Alternatively, we could, instead of working in the desirability framework, just work with partial preference orderings, but now not go the full monoset route where we are transitioning to just looking at propositions, but instead we modify our state space so that we keep gambles around, but now we have the ability to encode in our preferences views about how our choices affect the states. So everything as before, but now you might attempt to enrich the set of gambles so that we don't, we now include partial gambles generated by restricting the gambles in L omega to events, to our choice events. So we've got partial gambles that are defined on the space where we restrict to the case where we've made a particular choice, and then we close that set of partial gambles under function addition and scaling. And because that set of conditioning events is a partition of the space, that kind of closure isn't a problem. And then you might attempt to axiomatize coherent partial conditional preference preferences on these partial gambles, and then generate verdicts about which gambles in the original space the agent will prefer based on her views about the preferability of their proxies in this bigger space once you take on board the information that you've chosen that gamble. This is a kind of approach that in spirit is similar to what Suppes and Zanotti did in axiomatizing giving a representation theorem for full agreement with a coherent conditional probability. So the point is that there's a kind of precedence for this, but Suppes and Zanotti are also looking at full agreement with a coherent conditional probability. And again, to the best of my knowledge, nobody has given an adequate axiomization of coherent partial preference relations of this sort. Lastly, just to plug another philosopher who's done some work on this, you might try to model this in a quite general IP framework, namely the probability filter framework that Catrin, Campbell-Moore, and I started thinking about a long time ago, and Catrin has since developed quite extensively. So the thought here is that we're going to have the same set of gambles on our refined space here. Now we're not going to look at partial functions, just the set of all bounding gambles on this refined space. And then consider the set of all linear provisions on that space. And then we're going to take filters of linear provisions. So a subset of the power set of coherent linear provisions. So this is a set of sets of coherent linear provisions is itself coherent if it's a proper filter. That is, it's non-empty. It doesn't include the empty set. It's closed under supersets. And it's closed under finite intersections. And that amounts to forcing agents to draw out finite consequences of their probabilistic beliefs. And you can connect these filter representations up with rejection functions as follows. So let's consider this rejection function, which is defined from finite subsets of our space of gambles to finite subsets of our space of gambles. You can take an e-admissibility type approach to rejection, where you say you reject a gamble just in case the set of coherent linear provisions that informally they all think some element of the set is better in the evidential decision theory sense than G, but they might not agree on which one is better. Or you could take a maximality approach and reject a gamble just in case there's a single gamble that they all agree is better in the evidential sense. Okay, this is a quite straightforward, the flexibility of this framework, I think, is apparent here. The generality of it is apparent. It allows you to quite straightforwardly incorporate the insights of evidential decision theory without having to rework things too much from the ground up. Okay, so that's where I'll leave the discussion of evidential decision theory for the moment. The point here was not to try to drive home some particular message, but just to canvas some different ways in which you might try, as an imprecise probabilist, to incorporate some of the main insights of evidential decision theory. Let me briefly move to causal decision theory and ask, okay, we're almost out of time, so I will try to make this relatively quick. I'm not going to go through all the same moves for causal decision theory, but I do want to note causal decision theorists also agree in the protection case that you should buy the protection. They agree that if you buy the protection, you're likelier to end up in one state than the other, and that's why you should buy the protection, despite the fact that on the surface here it looks like you're violating dominance. But the key is that where for the evidentialist, they say you should buy the protection because buying protection is good news that your window won't be smashed. The causalist says you should buy the protection because buying the protection makes it the case that your windshield won't be smashed. It causally influences the state of the world. It helps to bring about the state in which the windshield isn't smashed. And there are cases in which, as we know, causal relevance and evidential relevance come apart. And in those cases, evidential decision theory and causal decision theory will yield different verdicts. So to give you an example of one of these cases, consider a version of Prisoner's Dilemma, but where you're playing with a twin. You are psychological duplicates of one another. And so as you're deliberating about what to do, you're getting evidence about what your twin will do. And so if you're an evidentialist, you think, well, suppose that I learn that I rat. That's great news that my twin ratted. And so it's great news that we're both going to end up with 10 years in jail. Suppose that I learn that I stayed silent. That's great news that my twin stayed silent. And so it's great news that probably will only get 1 year in jail. And for that reason, evidential decision theorists in the twins' prisoner dilemmas say that you should stay silent. Causal decision theorists in this case will tell you to rat. Why? Presuming the standard setup where you're being grilled in a totally different location from your twin, what you do, what you choose, has no causal impact on what your twin will choose, and so these states are causally independent of your action, and in that case, dominance reasoning is perfectly valid. And since, oh, sorry, that 20 up in the corner should be a negative 20 to actually get dominance here. But I suppose you all knew that. So silence dominates ratting. Sorry, I've drawn this entirely wrong. You're starting to see the meme of the horse being drawn well at the beginning and very poorly at the end. But imagine the payouts for Prisoner's Dilemma. So you should go free in that case where you rat and they stay silent. And in that case, ratting dominates silence. Apologies for that. But the point stands. In cases where your act is a harbinger of good news, but not via the causal consequences of the act, then evidential and decision theory will come apart. And causalists like Jim Joyce say that what you should be concerned with, what a rational decision maker is concerned with, is doing the most to make the world good, doing the most to bring about utility. And in the cases where there are these kind of spurious correlations, they ought not impact your decision making. I'm not going to go through Jim's representation theorem, but I do want to note that Jim takes a very similar, in a book called The Foundations of Causal Decision Theory, takes a similar approach to Jeffrey. But instead of yielding representation in terms of an evidential expected utility operator, yields a conditional expected utility operator, but the conditioning is a different kind of conditioning. It represents not standard conditionalization, but a kind of supposition that tracks our subjective suppositions. So the axiomization is meant to make sure that the kind of supposition that you're engaging with is asking the agent roughly to consider not what happens, not what she thinks about the world if it turns out that she performs this act, which coincides with the news value, how good it would be to learn that she's performed this act, but instead asks her to consider how good the world would be were she to perform this act. So this supposition, this double line supposition, is a kind of subjunctive supposition. One reason you might end up being more optimistic about the prospects for incorporating the lessons of causal decision theory into IP is that the kind of representation that Joyce gives can be rewritten in terms of an imaging function. You can factor out from that suppositional probability function an operator that's called an imaging function. And what it does is at each world, it yields a PMF. The given an act proposition, it yields a PMF that puts all its probability mass on the event where you perform A. So roughly what it's capturing is the probability at a particular world that you would end up in some other world were you to perform an act, were you to make a proposition true. And given that, if we start off, say, in the desirability framework with some of these components, so we start off with, we're not, in this case, deriving a linear utility the way that Jim does, but we, in the standard desirability way, let's say we help ourselves to that. Let's say we also help ourselves to an imaging function that tells us what the effect of intervening to make A true, or at least what would happen were you to make A true, how probable it would be that you would end up in other worlds. And you start off with a coherent set of desirable gambles. Well, in that case, you can read off, you can repackage that imaging function into the gamble and take an unconditional expectation with respect to that. And now if we replace that precise unconditional expectation with a set of desirable gambles, we still have the subjunctive bit packaged into the gamble. So we can say an agent prefers a gamble to another just in case the effect of supposing that she would perform A on this gamble that specifies how good each state of the world is, that's better than what would happen were she to perform B. Okay. And those are just regular gambles that you could represent in the gamble framework. So you don't need anything like interval dominance to make this work. Now, this still might not be the way you want to go. Maybe you want to just take the kind of relation, work with partial preference relations, but try to axiomatize it in a way that doesn't assume totality. That would be the kind of most straightforward way of getting an imprecise version of causal decision theory. But the point is just that it's not as hard to incorporate this into the desirability framework as it is for evidential decision theory. All right. Now, the one last thing that I'm going to touch on, and this is actually kind of quick, so I won't keep you here too much longer, shifts gears. It has nothing to do now with how to try to generalize our decision theory to do away with act-state dependence. Instead, the question is really what are we buying ourselves by allowing, other than being more maybe psychologically realistic, to be able to model Kevin's opinions, and Kevin actually has incomplete preferences. So other than that kind of psychological realism, or some kind of value that we attach to respecting the evidence, if we are not so moved by considerations of evidence, and all we really care about is getting utility, what is the value of ending up with incomparability in our choice function. So here I'm going to move away from desirability and just think about choice and choice functions. So imagine the question is this. Imagine that we are we're a team tasked with evaluating some forecasters. These forecasters somehow synthesized their best data and gave us a choice function. And we distributed that choice function to, I don't know, lots of little organizations across the country that made decisions on the basis of that choice function. And we don't know exactly what choices they faced. So we don't know exactly how things turned out for them. But now, ex post, we do know what state of the world we're in, let's say. And we want to evaluate these different forecasting teams that gave us these choice functions and say, well, can we say anything about who did better? So this is the framework that we're going to use for this. Consider again a finite possibility space. Consider all the finite subsets of gambles on that space. Let our choice function consider any choice function that returns a subset. So we're faced with some finite number of gambles. Our choice function returns some subset of that are choice-worthy. And let's say we also have a measure on this space of decision problems that we might face. So we don't know which of all these organizations that we distributed the choice function to, we don't know which actual decision problems they faced, but let's say we know that there's a particular probability distribution over that set of choice functions. And it doesn't matter what measure this is. The result will be exactly the same, whatever measure we choose, as long as it is not too extreme. So again, the question is, if we know the state of the world and we know this measure on the space of decision problems, but not exactly which decision problems C was used to address, can we say something? Can we evaluate how well C did in that state of the world at guiding choice? This is the kind of question that Teddy is very familiar with, and that Shervish discussed on the back of Savage in the late 80s. I'm going to focus on a version of this argument that Richard Pettigrew and Catrin Campbell-Moore are currently thinking about. This might not be fully faithful to their particular rendering, but I think it gets the heart of the argument across. So to answer the question of what kind of guidance value the choice function provided, we have to say something about what people did with it when they faced incomparability. And Pettigrew takes a particular choice. He assumes that decision makers randomize over their choice set. So if the choice set is some finite number of gambles, then there is some probability mass function according to which they selected a member of that choice set. Now that probability mass function that they're using to randomize could change from decision problem to decision problem. That's fine. But what they're doing is just randomizing. And then we're going to take the utility of the choice set to be a vector. The vector is the payout of each of the gambles. The utility at a world of the choice set is the vector of payouts of the finite number of gambles in that choice set. And then the expected payout of the choice set at that world is just the expected payout according to whatever randomization process they're using. So that's the expected payout at omega if you're randomly picking from the choice set according to that probability mass function. And then what they suggest is measuring the guidance value by the expected payout. So we don't know what gamble they're going to face, but we do know what the choice function recommends in any decision problem. And we do know that they're going to randomize in some way between the things in their choice set. And so we can take a kind of expectation of that. And that's it. Richard's And Catrin's challenge is this. They think no reasonable choice function should be dominated in terms of guidance value, but every imprecise choice function is dominated in terms of guidance value. And so every imprecise choice function is unreasonable. Big words. I don't know that they would actually put it like that, but I'm trying to be a bit polemical right now to get us to care about this, since I want to defend imprecise choice functions. And the reason is quite simple. When we measure guidance value in the way that we just outlined, then so long as the measure, it doesn't actually require anything this strong, but let's say that the measure puts non-zero measure on every non-degenerate set of decision problems. The space of finite sets of gambles comes with a metric, so we can talk about the topology and measure induced by that. So that's what I mean here when I'm referring to non-degenerate sets. Then it turns out that for any probability mass function, it will expect its own choice function, that is the set of Bayes optimal options relative to that probability mass function, to be best, unless the other choice function differs from it on merely a set of measure zero. So it is strictly proper in that sense. And then we can use a sufficiently generalized version of Wald's complete class theorem to show that the Bayes optimal choice functions are exactly the non-dominated ones. I don't provide enough detail here for you to really reconstruct that, but Wald's complete class theorem, and I have to thank Teddy for impressing this on me years ago now, is really much more general than philosophers have given it credit for, and really I think sits at the heart of all scoring rule based evaluations, results that involve scoring rules. But in any case, these two things together yield Richard and Catrin's argument. Why? Because strict propriety means that only the precise choice functions are Bayes optimal, and the complete class theorem says, well, then they're the only admissible ones. And that's it. So what do we do? Well, it seems clear to me that randomizing is the weak point in this argument. Actual proponents of IP seem to either use conditions, criteria that aren't randomization but that come with problems, or better, in my view, use the fact of incomparability as a sign that you ought to gather more evidence. And it's there that I think we need to do more systematic theorizing. I think we need to specify, try to say more rigorously what sorts of methods for resolving incomparability put us in a better position than precise Bayesians, and in exactly what sense it's a better position. So we need to sort of, when the rubber meets the road and it comes to getting utility, we need to say something more about what we're doing to resolve incomparability and how that helps us outperform precise Bayesians in at least some class of decision problems in practical terms. So that's it. I'll end there. I know I've gone over a little bit, but thank you for your patience.